Elasticity and Hooke's law is our new topic we are going to see, but please don't forget to subscribe to the channel. Okay, if you want all the topics about the math from O level to A level, advanced level, you go to the playlist, all those topics are there. So, elasticity, of course, we are going to deal with elastic things as I have an example here. We are going to see when we are going through these things here. Okay, we are going to consider the behavior of springs. I think we need spring, then a string, which is elastic. This is a string, but it's elastic. The unstretched length of an elastic string is called the natural length. Now you see here, I've not stretched. This is what we call the natural length. You are going to see what happens if I stretch it. Okay, what does this law say? It says that the tension in a stretched string is proportional to the extension of the string from its natural length. We'll start the diagrams below. Here is before stretching. There, before you stretch, we have what we call the natural length. Then after stretching, we have that extension. Now, look at this. This is my natural length before I stretch. So it's the same here. But now, when I stretch, you see I'm stretching this. I'm forming an extension. That extension I'm forming is what we call from our natural length. This extension I'm forming is what we call this x. From the natural length, this extension we made is what we call the x. But when I stretch this string like this, there is some tension you see that is pulling this string to come back to its to its natural length. So this tension is acting this side and is also acting this side. So there is always tension in that elastic string. So x here stands for our extension after the stretch. L stands for the natural length. Then T stands for the extension. As you see, when I pull it, it's pulling itself back. I think you can see. It's pulling itself back. So that tension that is pulling it back is what we call the tension. Then lambda is the modulus of elasticity. Remember, if something is proportional, we always introduce in the proportional constants, as you see. Now, always our tension is going to be equaling to the modulus of elasticity times the extension of that we made over the natural length. So from there now, we can know that when x is L, so if the extension we've stretched is equaling to the natural length, it means that the natural length of the string after that becomes now 2L. Now, when this is L and this is L, it means that now the natural length of the string, if this is L, and I stretch it at L still, now the the length of the wall now is from here up to here. So it becomes 2L. When the extension is twice the natural length. When the extension is equal to the natural length you had before. So when we have that, it means that the length now of the whole string is going to be 2L, because we are going to add this L plus now this new L, because this one has been stretched to a length equal to this. And so now our new length, that's why it's 2L. Remember, from here now, if we substitute our x equal to L here, and now our L is twice the original length or the natural length, and we put them here, L is now 2L, then x is L. So when we divide and multiply this two here, is that our modulus of elasticity is equal to twice the tension in the string. So what does that tell you? This implies that the modulus of elasticity is equal to the tension required to double the length of the string. So always this modulus is twice the length, the tension required to double the string. So required to double the length of the string. As you see, this T, 2T, is going to be equal to lambda. If you add this to T, if you are making the length twice the original length or the natural length. Okay, lambda is measured in newtons, x and L they are measured in meters. Let us go now to springs. Now the difference I failed to access the string, but I'm going to show you here. Assuming this one is my natural length. Now, when I compress it like this, for a spring, you're going to see it's going to raise, get compressed, Then there now is that the extension is going to be negative because we are compressing. Okay, when springs are stretched, we also apply a slope. If you stretch that spring, the same applies to elastic string. A spring and a string are different. This is a string. A spring is like that. That thing that is like coil is coiling around. That's what we call as spring. Now, when they are compressed, then they exert the thrust outwards. T is the thrust and X is the compression, and also apply to slope. At this time, the tension is no longer we are going to use. I'm going to use what we call the thrust. So if this is the spring before compression, when you compress it, I think it's that even the distance between the spiral we are going to reduce. So we are compressed from here up to now. This X we have reduced to is going to be the compression. Then this T is going to be the thrust. Remember, as we are pushing, it's also trying to. Okay? So that's the idea we have there. So now we are going to use also the same formula, but this is going to be for the thrust. X is for the compression, then L stands for natural length. Basically, that's what we had there. So let's see an example. These are basic examples, of course, to show you how we can use the formula and on before we move to serious ones. An elastic string of natural length 12 meters has modulus of 40 newtons. Find the tension in the string when the extension is 60 centimeters. So, in our solution there, we summarize the equation. They are giving us L, the natural length, is equal to 12 meters. And then they are giving us modulus of elasticity as 40 newtons. Now they want us to get part A. Find tension when the spring is stretched to 60. Now it's that the extension is 60 centimeters. Now you convert it to meters because this one is already in meters. So our X is equal to 60 centimeters, which is going to be the same as 60 over 100. Now this is in meters. So our X is going to be 0.6 meters. Really easy. So after having our X, now we apply our formula here. So our T is equal to lambda X over L. We have this, we have this, we have this. So our tension is going to be our lambda, which is 40, times the extension in meters over the natural length, which is 12. So from here, our T is going to be so I'm going to be having 2 newtons. So the tension there is going to be 2 newtons, which is. When I count out part B, in part B they are saying find extension when the tension is 30 newtons. So they want us to get now X. Still, now they are giving us tension as 30 newtons. Remember, it's the same string, meaning this is going to remain the same. This is going to remain the same. So L is 12 meters and our lambda is still 40 newtons. So using our formula T equal to lambda X over L, our tension now we have it as 30 equal to 40. Now times the X, we don't know, over 12. I think we can see this one and go. Then by this one, by this 3. So this one is going to give me 3 times 3 will be equal to my X. So my X is going to be 9 meters. So if you want, you can convert them to centimeters by saying X is going to be 9 times 100. Now it is in centimeters. So X is going to be 900 centimeters. Because they were giving us expressions in centimeters. You see, with these are very easy things as we are going to see. So that's the example. You're going to see more the next lesson. I wish you well, but please don't forget to subscribe to the channel.